Welcome to this next video of the reverse engineering course of simplilearn security. This video is associated with chapter number 9 of the reverse engineering course. In the previous video, we came across an application that was accessing some values and keys inside the Windows registry. This time, we will examine an application that tries to locate a specific file inside the system, access the file, read its contents, and validate them upon a specific custom algorithm, which we will of course analyze in detail in order to do some more practical reverse engineering. During the written part of this chapter, I didn't show how to locate the function that contains that algorithm. This is because you should be already able to locate this function by yourself using the knowledge you acquired in the previous chapters. Now in this video, I'm going to show all the steps. However, what I recommend is that you first try to do the first step by yourself. In other words, locate the function that contains the algorithm that we are going to analyze, and then come back to this video. So let's proceed by running the application. We can see again that it just says that valid data was not found. It just displays a status message. So let's try and load the application in Knowledge Debugger. So let's do a quick search for string references. We can immediately see a reference here. So this is the instruction that references the memory address where this string is located. And we can see here the conditional jump, that if it is executed, it's going to display this message application, otherwise it's going to display this one. And we can place a breakpoint on the first call that we made going backwards. And I'm going also to place a breakpoint at the beginning of this function. Sometimes, when analyzing an application, it would be very useful to know from where a function is called, because in that way we can also trace back the execution in using another way and not just the stack, and also understand better its design. So we can just right click, find reference to selected command. Now in this case we don't find any reference. This is because this function could be called indirectly by using an address that is passed to a register and then, for example, doing call ex, which means that in that case, if we manage to break at the first instruction, we can then locate from the stack the address from where this function was called. So we're going to see this in practice. I'm going to run the application. Now, as you see, we stopped here. And let's see what the stack says. It says return to this address here. And we know that at this point the return address, before the stack frame is prepared, is at the top of the stack once we enter. So let's double click here, or better following this assembler, and we can see here that that function is referenced indirectly using a register. So if we were trying using another way, let's say as we did before, by searching for references to the first instruction of that function, we wouldn't be able to locate it. But now, by stopping at the first instruction, we can then see at the stack the return address, which is, as we know, the address immediately after the call instruction. So now we know from which address that function is called. And we can now proceed by analyzing this function. So let's run the application. And now we're going to stop at the next breakpoint. And let's step in this function here. let's see what we can observe. You can see here a file called, actually the name of a file called learn then .dat, and we can see a call to this API here, the get system directory, which returns the path to the system32 directory. Then we can see a call to create file, which is the most commonly used API in Windows in order to obtain a handle to a file. Then we can see a call to get file size, which returns in EX the size of the file, in case, of course, the handle returned by the create file is valid. And then we can see a call to an API which is called read file, which is going to put in a buffer the contents of that file. And then we can see more instructions here. But initially we just take a quick look at the API's code, when this is possible to do, in order to understand more or less what is going to happen in the next steps. So let's start stepping over the instructions. You can see at this point that it's going to call the get system directory. You can see at the stack the parameters, the size of the buffer, and this is the address of the buffer, so we can just follow in dump and then choose this type of formatting in order to see the contents written in the buffer while we debug it. So let's step over, and you can see now the directory path returned in this buffer. And let's see now what's going to happen. Now it checks if the byte at which edx points to, which now edx points to the name of that file. As you see now, of course, this byte is not 0, and is going to loop up, is going to place into edx the address where the directory path is stored. Then in ECX is going to set a constant, which is 13 hex. Then in EX is going to place the address of the memory where the name of the file is stored. Is going to read the first byte to EX, and then is going to store that byte at edx plus 13, so we can follow it down memory address to see where it's going to write this. So as you're gonna see, it's going to append it to the directory path, increase this value here, then this, and then go up. As you can see now, EX points to the next character of the file name. It reads that, and then it's going to write this and append it in the directory name. So you're gonna see how it appends the file name to the directory name to create an absolute path to that file. So the next API that's going to be called is the create file, So let's continue stepping over. We can see here the parameters. So this is the file name, the absolute path to the file. It's going to ask for only read access, and it's trying to locate an existing file. It will not create a new one if it will not find it with the same name. So if we step over, we're going to see that EX now contains an invalid handle value, -1, which means that it didn't manage to locate the file. So I'm going to set a breakpoint here, continue stepping, and you can see here that the value returned from EX was stored in this local variable here, and then before going and check the size of the file, it checks if the return value, which was stored in this local variable, is -1, which means that it didn't locate the file in the first place. So this jump is going to be executed. EX is going to be zeroed out. We're going to return back. So this jump is going to be executed, and the valid data not found message is going to be displayed. So let's run the application again. Okay, so we run until we break this breakpoint here, and before now this API is called, I'm going to manually create that file. And let's now step over. As you can see now, the return value in EX is the handle number. So let's continue. So now this jump is not going to be executed because the value returned in EX was not an invalid handle. And now it's going to call the get file size. Let's see what happens. Let's step over, and we see that the size returned in EX is 0. That's because the file is empty. And then it's going to store the size value into this variable here, EBP -18, and then compare that value with 10 hex, which is 16 in decimal. Of course, this doesn't match, and we know that it's going to happen. So I'm going to place another breakpoint here. I'm going to run the application again. And now I run until I break here. So we know what is the correct size that the file should have. So let's go back, open the file with Notepad, and this is an error message box that says that Notepad cannot access the file. This is because, if you remember, when this API was called, the share mode was set to 0, which means that for the time that this process, the process of the application, has an open handle to that file, no other process can access it. So what we can do is to restart the application. Before doing anything else, we're going to access the file again, and we're going to write 16 characters, 16 bytes. Save. And now we can continue the execution until we break here. So let's step over. We see the value returned in EX is 10. So this comparison is going to be true. And we can continue stepping. So let's see now what is going to happen. We see that at this point it's going to call the read file API and is going to place the contents in this buffer here. It's going to read 10 bytes, and we can see the first parameter here, which is the value of the handle of the file for which we requested the access. So let's see here which is the buffer that we're going to see the contents of the file written. Let's step over and we can see now the contents of the files written in this buffer. So we want to place another breakpoint here. So everything went alright. So this API returns 1. Here you can see that. Otherwise it would return null, which means that something went wrong. And then we can see here that a slightly complex algorithm is going to start, which we are going now to analyze in detail. We can see here that in this local variable is stored the buffer address where the data read from the file is stored. So it's going to pass this address to EX. So let's step over. We can see that now EX contains the address of this buffer. And then it's going to place to DL the byte that EX points to, which is the first byte. So we see now that DL is 31. So what we know is that in this local variable here we always have the address of the buffer of the data read from the file. So then it's going to put to AL the address of the buffer plus 2. So actually it's the third byte. Remember that we always start counting from 0. So it's from the first byte plus 1 plus another 1. So the third byte. You see? So now we have in EDX 31 and in EX 33. The first and the third byte in hex. Then it makes an addition of these two. Then it moves to AL, the second byte of the buffer. Then it moves to E6, the fourth, adds another addition, and then compares the value in EDX and DX. Now remember then that EDX contains the sum of the first and the third byte, and EX contains the sum of the second and the fourth byte. So actually what the algorithm says is if the addition of the first and the third byte equal the addition of the second and the fourth byte, then continue, otherwise it will just jump and arrive here, and we know that game over basically. So let's start taking notes of what we see. Because it will help us a lot during the analysis of the algorithm. So let's see what we know by now. We know that the length of the correct let's say code is 16 hex. Let me put this in capital. And that the first plus the second byte must equal, the first plus the third must equal the second plus the fourth. Now, in order for you not to be confused, I'm going to use exactly the same code that I was using also during the written part. So here I should have put a 0, but anyway, what I'm going to do now is just to restart the application. And yes, before doing anything, I'm going to open this with Notepad, and I'm going to use exactly the same code that I used in the written part. So that you don't get confused. So the code that I'm going to use is this one here. And you can see now here the correct code, not the correct one, I mean the same code as used in the written part, so that you can watch this video and read some parts of the chapter at the same time and by looking at the same things. So what we have in this case is 30 hex plus 32 doesn't of course equal 31 plus 34. So we need to fix this. So what we're going to do is, now I'm going to change this code in order to make this comparison work. So I'm going to change this like this, the first 4, so that the first plus the third equals the second plus the fourth, and I'm going to keep the rest the same. So now we have passed the first check. Now let's see what is going to happen during the rest of the algorithm. Now, in order to verify that this is of course correct, we can just, let's say, restart the application. Open this again with Notepad and put the new code here as it is at the moment and run. We can remove this breakpoint from here because we don't need it anymore. Also this from here. We can put a breakpoint immediately just after exiting that function. We don't need these breakpoints anymore. And I'm going only to place a breakpoint at the beginning of the algorithm. So let's go and see now what is going to happen. We see now in the buffer the code we just entered. So let's see that now the comparison matches. You see, EX and EDX are the same, so now it's not going to jump, and it continues with the second part of the algorithm, which practically what it says is that it reads the 5th byte and the 7th byte, stores their sum in EDX, then reads the 6th byte and the 8th byte, stores their sum in ECX, and then compares the two values, EDX with ECX. So what the algorithm says is now that the 5th byte plus the 7th must equal the 6th plus the 8th. In this case, though, we have 34 plus 36, which of course doesn't equal 35 plus 37. So we need to change. We keep the first 4, and we need to change the next 4 in a way that they match this comparison here. So we take the next 4 and we can change in order to match that the 5th plus the 7th equals this plus this. You can change this to 3, and we copy and paste the rest of the code for now as it is. So now we pass also the next check, and we can verify this. I'm going to set a breakpoint here at the jump related to the second check. I'm going to start the application again. Just change the code with a new one and see if it passes now. So it passed the first check, so we arrived here, and as we see, EDX, ECX match, so we passed also the next check, and we can continue analyzing the algorithm. So let's see what's going to happen now. It's going to read the 9th byte, the 9th byte, and then the 10th. Is going to calculate their sum. This is the sum. And then it's going to read the 11th byte and is going to compare the sum of the 9th plus the 10th byte if they equal the 11th byte. So what the algorithm says is that the 9th byte plus the 10th must equal the 11th. But what we have right now is that 38 plus 39 doesn't equal 41, which is the hex value of A. So we need to change the algorithm again, and replace A with Q, which is the character for the addition of 38 plus 39. The hex result corresponds to this ASCII character. So here in E6, if you just right click and do modify, you're going to see that 71 is the character Q lowercase. So we managed to pass also the next check. Now, instead of reloading every time the application, we're going to fool it so that it thinks that everything was correct in the first place. So I'm going to modify EBX with the correct value, so we can continue analyzing the algorithm without having to restart. And then once we finish the analysis of the algorithm, we are going to test the final code that we are going to create against this verification algorithm. So let's proceed with the next check. So as you can see, it reads in DL, the first byte, and then checks if the first and the second byte are equal. But if they are, it's going to exit, going to arrive here, and this will be game over. So in reality it doesn't want that the first and the second byte are the same, which are not. So we have already passed this verification check. So it's going to continue. Then it's going to check if the 5th and the 6th bytes are the same, which are not again. So we passed also this check. Then it's going to do another interesting check at this point here. So let's see what's going to happen now. As you can see, it reads in DL the 12th byte and checks if it is less or equal to 39. if it is, it's going to bypass all the rest of the checks and come here, so it's game over, because it's going to zero out EX. And then, if you remember well, if EX is 0, it's going to display the bad boy message. Otherwise, we're going to arrive here, and then this jump is going to bypass the zeroing of EX and then exit the function. So the 12th byte has to be greater than 39, and it has to be also less than 41, which is not. That's why this is going to jump. So what we have at this point here is that the 12th byte has to be greater than 39 hex and less than 41. But at this point, the 12th byte is the character B, which maps to 42 hex. So we're going to change B with a colon, which maps the at the hex value 3A. So we're going to trick the application thinking that this was alright, and I'm going to set new origin here in order to continue the execution after this check. And let's see now what is going to happen. We see that it reads the 13th byte, and if the 13th byte is less or equal to 5A, in this case is 43, this check is going to fail. So we don't want this, and let's trick the application again and continue from here. And then it's going to check again the 13th byte, and if it is greater or equal to 61, it's going to jump. So this check didn't fail, but the previous did, so we have to fix this. So what the algorithm says that the 13th byte has to be bigger than 5A and smaller than 61. But at this point the 13th byte is character C, which maps to 43 hex. So the second comparison is true, but the first one is not. So we're going to change the code again. The bracket here. Now the bracket maps to character 5B. I have the ASCII table in front of me, so sorry, this bracket here. So now also this check is okay. The algorithm at this point has taken this form, and we are ready to continue with the rest of the algorithm. So let's continue stepping over the instructions. We're going to see now that it's going to read to AL the 14th byte, and it's going to check if it is, in case it is less or equal to this value here, 7A is going to jump and this game over. It is, because we see that the 14th byte is character D, which maps to 44. So we're going to take the application to continue here, and then it checks if the 14th byte is also bigger than 7F, which is not. So the second check according to the algorithm is okay. So what the algorithm says is that the 14th byte has to be bigger than 7A and smaller than 7F, but what we have here, the character D maps to value 44 hex, so the first check will not be verified. So we're going to change the algorithm again and change D with this curly bracket, which maps to character 7D. So it is bigger than 7A and it is less than 7F. So we also now pass both of these checks, and this is the form of the code at this point, and we can continue and see what is going to do now with the 15th byte. But before continue, let's just write down here that this character we entered before to pass this check that was failing maps to 7D hex. So it's going to read the 15th character to DL, and then it's going to compare if this value is less or equal with 7A, which it is, but if it is, then game over again. So we need a value greater than 7A, and according to the ASCII table, in order to pass this check here, we can use another character, and now in this case we can change E with the other curly bracket, which it's 7B, this curly bracket here maps to character 7B, which is greater than 7A. So when we are going to check next time, it's not going to jump. So we can trick the application to continue from here, and we can take a look at how the code looks like at this point. So since we arrived here and this is the last check, it's good to try the code as it is to this point and see that the rest of the checks are okay. So let's go and yes, we need to restart the application in order to be able to access the file. Let's paste the code as it is at this point and let's run. Let's start stepping over. We see we pass all the checks before, also this one. So let's now see what is going to happen during the last check. So as you can see, now it's going to read to AL the 15th byte, 7B, this one here, and then it's going to XOR that value with the value of the 16th byte, F, which is 46, and then it's going to check if the result is 17, which is not, is 3D. So the last check is not going to be verified. So what the algorithm says is that XORing the 15th with the 16th byte, the result must equal 17 hex. At this point, the 15th byte is 7B, so we can change the 16th byte with something that we don't know yet in order for the final result to be equal to 17 hex. So what we can do, we can invert this and say 7B XOR 17 and find what is the result. So 7B XOR 17 is 6C, and according to the ASCII table, the value 6C maps to the letter L lowercase. So the final code should be this here. So let's copy and paste this into the file and let's run. We see we pass all the checks correctly and we also pass the final check. So we see that the application is going to close the handle to the file because it doesn't need it anymore. It's going to put 1 to AL, so you see EX equals 1. It's going to jump, so it is going to skip the zeroing out of EX. So when we return back, EX is 1, so this jump is not going to be executed, it's not going to be effective, and just run valid data was found. So during this video we had the chance to go through a more complicated algorithm and also play a little bit with the execution of the application. For example, you saw that we can redirect the instruction pointer to another instruction in order to bypass an effective conditional jump that we don't want to follow. And as you saw, we can also directly modify a value on a register in order to match the value that the algorithm is looking for or that we want to match. And we also had the chance to look around something that was not very straightforward from the beginning, and we broke it down into several steps by taking notes, which is something that you should do in cases like that, and of course in more complicated cases, in order not to lose track of what is going on. So I hope you had fun again, and see you in the next video.